Hello again, this is the Pencrest High School AP Physics C video series. This is video 2E, friction as a positive force. So we are used to friction being a negative force, meaning that it typically acts in such a way as to oppose motion or impending motion. We're now going to see that friction can actually be a positive force. It can act in the direction of motion. This usually happens when we have multiple objects in a system related to the application of Newton's third law. So we'll consider the system that's shown below. We have a block M1, and it's resting on top of another block M2. We're going to say that the surface M2 rests on is frictionless, but between the two objects there is friction. So between M1 and M2 there's static and kinetic friction. The objects are going to accelerate to the right. For the time being, we will assume that the objects accelerate together. That is, M1 doesn't slip off the back of M2. The question is, what is it that makes M1 accelerate to the right? And the answer is friction. So, despite the fact that the two objects are moving, they are moving together. So there's no relative motion between M1 and M2. And that means that static friction is acting between M1 and M2, which is what makes M1 move to the right. So we will construct a free body diagram of each object. If we look at M1, the normal force and the gravitational force are sort of standard. There is a static friction force that's pulling it to the right, making it accelerate to the right. And if we look at M2, again, we have a normal force acting up. We also have the normal force from M1 pushing down on M2, as well as its own weight, M2 times G. The applied force on M2 acts to the right, and then we see the same friction force that is pulling M1 to the right is pulling on M2, but in the opposite direction, to the left. We want to make a note that this friction force is effectively an action-reaction pair between M1 and M2. So the friction acts to the left on the bottom block, opposing its motion or dragging it back. That same force acts to the right on the upper block. We'll note also that the friction force between the blocks is the only force acting in the x direction on the upper block. In other words, that's what has to make it move. We're going to then treat this as we would any other system with multiple objects. We write a force equation for each object, combine them. What we'll find is that the friction force acting between the blocks is the one that will drop out. So it behaves like tension or contact force does when we have multiple objects. So now we want to take a look at how we know if the upper block M1 is going to slip off the back of M2. If we pull hard enough on M2, we can effectively pull it out from under M1. But we have to do that in such a way that we exceed the maximum static friction force between the two objects. So when we look at that maximum friction force, that maximum static friction force, that's mu s, mu static, times Fn1. So that's the maximum that's available between the two objects. When we look at the force equation for M1's motion, when we set the maximum friction force equal to ma, again, it's the only x direction force. Fn1 is equal to m1g. So what we have is the static friction force equals ma. We would see that the m1 would drop out, and the maximum acceleration that these two objects can have and not slip relative to each other is mu static times g. Using that maximum acceleration, we could then find the magnitude of the maximum applied force that can be exerted and still have the objects move together. Again, that would be using the combined force equation where the static friction force drops out, but knowing what the maximum acceleration is for the entire system, we can then figure out what the maximum applied force is to have them stay together. So we'll see some examples of this. Next up is velocity dependent forces. You'll notice that we're going out of order a little bit, but we'll hit velocity dependent forces by the end of this week. Until then, enjoy. I'll see you again soon.